Hi guys, we're starting chapter 2 today. We're first going to do light. This one's also going to have 3 videos. They're not all going to have 3 videos per chapter, but I figure you'd rather watch them in short little snippets instead of like an hour-long video. So I hope y'all enjoy light, and as always, let me know if you have any questions. So there's some different theories, but all of it came along when quantum mechanics came along, and most of this research was done in the world wars. Okay, so we're talking early 20th century. They began investigating or researching small pieces that we now call quantum. Okay, so some things you need to know is that matter is very small, but we still need to see how it behaves on a macroscopic level, so just on that very large level. And electrons are the smallest subatomic particle that we're going to study. And so they're incredibly small pieces of matter. And much of the behavior of atoms is determined by electrons and only electrons. So we're going to learn some more about electrons. So the quantum mechanical model is going to tell us how electrons exist and how they behave in atoms. And we will be talking about them behaving as waves and particles, light specifically. Okay, so the quantum mechanical model is going to form the foundation of chemistry, and it's going to explain the periodic table and its trends, the behavior of elements in chemical bonding, and the color of atoms, but also their size. Okay, and this is directly related to other behaviors of electrons, like how elements are metals and nonmetals, and reactivities. So light is a form of electromagnetic radiation, which is super important. Okay, we will be talking about that a lot this chapter, and then it, of course, will appear back in our final. And again, it can act as waves or particles, and that electromagnetic radiation has an electric field, but also a magnetic field, and we'll see a picture in a minute. Also, don't forget about the speed of light. This is going to come up in calculations later. It is a constant, so you do need to know that. And light travels at a speed of 3 times 10 to the 8 meters per second, okay, which is 30 million meters per second. Okay, electromagnetic radiation. So here's that different electric field versus magnetic field. You're not going to be asked anything like this, but they are on different planes, those perpendicular planes. So one's like on the X plane and one's on the Y plane, if you think about a coordinate system. So parts of the wave are going to be important. You will need to know these, so make sure you understand. The amplitude is the height of the wave, from the center of the wave, which is normally called the origin, to the top or bottom. Also, amplitude shows us the intensity or how bright it is, the light. Wavelength, which we will write as lambda, and you'll see me write them as that. That's a Greek letter. That's the distance covered by one wave, and it is measured in meters. Okay, specifically, we're going to see some nanometers. And remember in chapter 0, I told you we'd use nano in chapter 2. So here's where it's appearing. It is from the top of one wave to the top of the next consecutive wave. It could also be the bottom to the bottom, the trough. This is also wavelength, but it's the same place in a wave to the next same place in the wave. Okay. And there's different wavelengths. Wavelengths give us color. And again, those different heights or amplitudes, they give us different brightness or intensity. So the colors, you will need to know the order of the rainbow, which is normally considered Roy-G Biv. So red, orange, yellow, green, blue, indigo, violet. And as white light enters a prism, it breaks into that. Actually, today it was raining and there was a double rainbow outside, which was really pretty. But it was because the light from the sun was hitting those water droplets. Okay, there's also something called frequency, which we denote as this V. I know that's kind of weird, but really it kind of looks like that. The font here is not the best, but it's also a Greek letter called nu. And frequency is just the number of waves that pass a point per second. Okay, we will see this as hertz. And sometimes I tell my students, because this is really the first calculations we do at the high school, that it hurts to do these problems. And so then they remember. But also, most of y'all know that the radio is in hertz. That's how they measure it. Also, phones are on different frequencies. And I don't know. I know my grandmother, who's 93, she does not like to wear her hearing aid. And it's because that frequency of her hearing aid interferes with the phone, especially now. So she likes to take it off when she's talking to us on the phone, but then she can't hear us. So it's kind of a lose-lose situation. So when there's the same frequencies, they're going to interfere with one another. It's also considered 1/, seconds. So you'll see hertz is equal to 1/, seconds, which is the same as seconds to the -1. Okay, you're going to see all these units. There probably will be a test or quiz question on units for frequency. So please make sure you know them just because there's so many different ones. Okay, the last one that we're going to talk about this video is energy. And this is proportional to the amplitude of the waves and their frequency. So the larger the amplitude, the more force it has. And the more frequency it is, the more force it has. So the more energy it has as well. So as we're doing these calculations, this is our main equation for wavelength and frequency. It's also very important that you know that they are inversely related, wavelength and frequency. So if one goes up, the other one's going to go down. So a really long wavelength is going to happen during a long period of time, so it has low frequency. It doesn't happen very often. But a really short wavelength has high frequency, so it happens more often. Okay, so again, those are an inverse relationship. That will be very important. Also remember this c is the speed of light, which is 3.00 times 10 to the 8 meters per second. All right. This is just a rearranged equation. If you need the rearranged one, please use that one. But just know I will generally use the original one. All right, so let's do a calculation. They want to know the wavelength. Again, in nanometers, I told you that was going to reappear. So let's go ahead and say that 1 meter is equal to 10 to the 9 nanometers. So there's 1 billion nanometers in 1 meter. So I've got, remember, this is our equation. I'm looking for wavelength. So we've got c over v. C is always a constant. 3 times 10 to the 8 meters per second divided by 4.62 times 10 to the 14. And this one they gave us 1/, seconds. So here it's easy to see that the seconds cancel. If you use hertz, it's not as easy to see. So just make sure you know which one you're using and that they're the same thing. Also, when you do this math, make sure you use that E button instead of the times 10 because otherwise you're going to need to use parentheses. So I get 6.49 times 10 to the -7, and that's in meters. But remember, it wants nanometers. So 1 meter is equal to 10 to the 9 nanometers, and this is 1 times 10 to the 9. And so I get 649 nanometers. Most light waves are going to be in the hundreds of nanometers. And the ones that we specifically can see are going to be between about 400 and 750 or so. Okay, that's just a little tidbit of information. Okay, let's do another one. This one gives us wavelength, but it's in nanometers. Remember, for our equation, it needs to be in meters. And it wants us to calculate the frequency. So frequency is equal to c over lambda. First, let's deal with our nanometers to meters. And I get 5.15 times 10 to the -7 meters. So I get 3 times 10 to the 8 meters per second over 5.15 times 10 to the negative 7 meters. And again, make sure you're using that E button. And I get 5.83 times 10 to the 14. And again, I don't care if you use 1 over seconds, seconds to the negative 1, or hertz, but you've got to use something. And if it were me, I would make sure you're consistent. All right, so let's talk about the electromagnetic spectrum some. Remember I told you we're from about 400 to 750 nanometers. That is the visible light that we can see. Everything to the left in this electromagnetic spectrum, sometimes they're flipped. It just depends on how they are. These are the non-harmful ones to biological systems. So infrared light is not harmful to us. Some examples of that are like night vision and heat vision, things like that. Microwaves, I'm sure you know about microwaves, but that's what most of us probably use to reheat food at the very least. And the radio waves, this is what all of our communication is in. So TV, cell phones, radio, all of that is in radio waves. Okay, I do want you to note that radio waves can be as big as skyscrapers. Okay, microwaves are in the centimeter range in wavelength, and infrared, they're smaller, they're less than a millimeter. Okay, but again, the UV is the light part of the spectrum is just such a small piece, that visible light that we can see, right? And then everything to the right of visible light is harmful to us. And remember, once upon a time, our ozone layer protected us from all the harmful radiation that came from space, although now we know that it does not anymore due to the holes in our ozone layer. Okay, so ultraviolet or UV light is the first one that's harmful. It's a little bit higher on the frequency than visible light. Okay, and you know we have different UVs. Some of you may know about UVA and B and now C, which is kind of common to talk about with COVID. X-rays, we all know X-rays can be harmful. That's why the people walk around the little barrier when they take your X-ray, or when you're at the dentist, they put a lead apron on you. And girls, I don't know if you've ever been to the dentist when you were pregnant, but they put 2 lead aprons over you just to make sure they're not harming the baby. Okay, and gamma rays, those are the most harmful. These are ones that come from nuclear explosions, nuclear radiation. This is, of course, the ones that made Hulk from a human into Hulk. That doesn't really happen, but there are mutations that happen through more of these. Most of the mutations that happen in the harmful range are mutations causing cancer, but there can be other mutations too, and we've seen that in the animals around Chernobyl and even the people in Japan. Okay. So again, that visible spectrum is kind of smack dab in the middle, but super tiny. Okay, because wavelength and frequency are inverse, the shorter the wavelength, the higher the frequency, and the higher the energy. So frequency and energy are directly related. So when one goes up, so does the other one. And just remember, the higher the frequency, the higher the energy, the more harmful it is. You will need to know the order because they're going to ask some questions based on those orders of the electromagnetic spectrum. So you can always go back and refer to that slide if you need to. Okay, so arrange these types of EM radiation in order of increasing frequency. Okay, and this is a good thing to do too, because sometimes y'all get confused on increasing and decreasing, and I just want to be very clear and make sure you understand. So increasing frequency means we're going from less harmful to more harmful. So the least harmful of this is infrared, and infrared is less than visible, which is less than X-ray. Okay, so the biggest one is X-ray, and sometimes they look like this with these less than or greater than signs. Okay, so I just need you to be okay with we're starting with the least frequency and moving towards the one with the most frequency. And just remember, the higher the frequency, the more harmful it is to humans and other biological entities. Okay, so this is A. B, because we're doing increasing wavelength now, remember wavelength and frequency are inverse. So the smallest wavelength is going to be X-ray. And then visible's in the middle. And then IR is next. IR is just an abbreviation for infrared, just as UV is an abbreviation for ultraviolet. Also, on the spectrum, please, please, please remember, IR is by the red side, and UV is by the violet side. Okay, so yes, really, purple color, and even that is pushing into that UV part of the spectrum, which could be more harmful. Okay, the photoelectric effect is next. So Einstein observed that when we shined light onto metal, sometimes the electrons got excited. And when this happened, they emitted photoelectrons, which is really kind of like energy. Or they used it as energy. And because of that, some of you may have calculators that have little solar cells on them, but they work inside. So those are not truly solar cells, they're photoelectric cells. So they're taking energy from your lights in your house or in your office building, and they're using that to produce energy so you're not running down the battery as quickly. Okay, so here we've got these energy equations. I do want you to know that really small packets are going to be called quanta, and they're packets of photons normally, specifically for light energy. They're delivered in packets, and again, that's called quanta, but we normally call them photons when we're talking about light energy. And this quanta is just a number. It's also a constant. We're going to call it Planck's constant because that's who was responsible for finding it. So here it is down here, Planck's constant, 6.626 times 10 to the negative 34 joule seconds. Okay, and this is E is equal to HV. That's if we have frequency. If we do not have frequency, but have wavelength, we're doing E is equal to HC over wavelength. Okay, it is important to note, again, energy is directly proportional to frequency, but it's inversely proportional to wavelength. Okay, so here's an example. This is a more simple example, and this is kind of how they'll be on your test or homework or quiz. Okay, there is going to be a more difficult example in a minute that I'm going to walk you through, but we're not going to have any like that on the test or quiz. So it wants to know how much energy is in this photon, and it gives me a frequency. So I need to use this top equation. I know they used F for frequency. This is one from a high school slide, so they use F for frequency there just for ease. So we're doing E is equal to 6.626, and again, that's Planck's constant, times 10 to the negative 34 joule seconds, times 6.65, times 10 to the 14 hertz. Okay, all we're doing is multiplying. Our seconds and our hertz cancel, so we're left with joules, which is our energy unit. We talked about that in chapter E. Sorry, 0. And I get 4.41 times 10 to the negative 19 joules. Okay, so it's not a lot of energy, but when you're thinking about it, we're talking about electrons and how much energy electrons produce. And remember, electrons are super, super tiny. Okay. Yep, sig figs matter. Don't forget that. This one, we're talking about meters. So we've got that wavelength. And here we want to know how much energy. So we've got to use this other equation. Planck's constant, always the same. It's a constant. Times 10 to the negative 34 joule seconds. C is also always a constant. 3 times 10 to the 8 meters per second. So at this point, my seconds is already canceling out, and we're dividing by 5.28 times 10 to the negative 7 meters. Remember, it is going to be common that wavelengths come in nanometers, and to do a calculation, they need to be in meters. And I get 3.76 times 10 to the negative 19 joules. Okay, again, super small. It is pretty common that if we're in that visible range, we're looking at 10 to the negative 19 joules. They may not always be in that visible range, though, y'all. We could be doing calculations for radio waves, and that's perfectly acceptable. Oh my gosh. Okay, so this is the more difficult one. Again, I'm just going to walk you through this. There won't be any like this on a test or a quiz. But there was one as extra credit on the homework. So just make sure if you want that extra credit, you can do it. If you don't, it's perfectly fine. Okay, but it says a nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? So we're going to do our equation originally with our wavelength. Okay, so they get our wavelength to meters. They do the equation to get the energy, and then they get it into joules, which is what our unit normally is. They also convert the millijoules they gave us to joules, and then they divide them because that tells us how many photons. Again, if you would like to attempt that question, you are more than welcome to, but there won't be any like this on the test or the quiz. Okay, there's 2 more examples. We're not going through that right now. All right, arranging them. We already arranged those specific ones, but there is another one. There we go. Okay, visible light. So this is important. Remember, I told you needed to know the order. So Roy G. Biv is going to come into play. This is the order. Red is the longest wavelength, and violet is the shortest. There will be test questions like this, so make sure you understand. So wavelength, our longest is red, green, blue. Frequency is going to be the inverse. I'm just going to write inverse of A. And then remember, energy and frequency are directly proportional. So I'm going to put same as B. And in a test environment where we were doing paper tests, which obviously we're not doing in this online environment, I would take those answers if you wrote inverse of A and same as B, or inverse of A and inverse of A. That tells me that you understand their relationships, which is super important. Okay, we're going to real briefly talk about the atomic spectra. This is really how scientists can tell what different things are made of, especially that are far away, like stars. Okay, also just in the atmosphere. Also, lights, especially neon lights, put off an atomic spectra. Fireworks, really anything that's bright and lights up, we can see their atomic spectra. So when you take an element and heat it up into a gas enough, it's going to give off light because you're giving it all this energy with heat. And it goes through the prism and it splits into different patterns. And it is important to note that every element has its own unique pattern. So hydrogen has 4 specific lines. And as you increase an atomic number of lines are going to increase as well. So here we see helium, which is atomic number 2, has 6 lines. But barium, atomic number 4, has many more than 6 lines. Notice oxygen and neon, these are different spectra. Instead of emission spectra, they're absorption spectra. So they're kind of inverse of the black background one. Okay, but all of this goes back to Bohr's model, which we'll talk about some, but not a ton. You may remember Bohr's model from even high school or middle school. So there's our nucleus. We've got rings. Let's say we're doing... let's say we're doing lithium. So lithium has 3 total electrons, 2 on the center ring and 1 on the outside ring. If we were doing a bigger one like oxygen, oxygen has 8 total electrons, 2 on the center, and then 6 on the outside. Okay, some of you may remember them. They pair first. That's not how they do that. We'll talk about that next video. Okay. And just remember that quantized amount of energy, that refers to Planck's constant. from this slide. Electrons have their specific orbitals that they travel in, like these, and they're stationary. That's what we go with. Again, this is Bohr's model. They're not truly stationary because when they gain energy, they jump up. Okay, and when they jump up, they are excited. Their normal state is ground. So there's an excited state, and then their normal location is that ground state. And again, to get energy, you've got to be able to jump up. And so they have to be given energy in order to do that. This is kind of like, so I love football. I don't know how many of you watched my introduction video, but you know, if our team is not doing so well, you may be sitting on the couch and kind of bummed out. But if something exciting happens, you've amazingly got more energy and you jump up and you cheer. Okay, or even if you're at a game in person. And so electrons are kind of like that. They want to be in their normal ground state until they get that extra energy. Okay, and that extra energy will eventually be given off. And when it's given off, it's normally emitted as light. Okay, it is very commonly emitted as light, which is how we get the different colors that we can see. Okay, the different drops give off different colors. Normally, the less it drops, the longer the wavelength is going to be. You're not going to be asked anything about that, but at a university level in a normal semester, that's 16 weeks, you would probably be asked to do calculations and determine the drop and how far it went. Okay. And that is it for today's video. I hope you enjoyed it. We'll see you next time. Y'all have a good day.